And of course, once you've got simple irreducible quadratic factors, why not have repeated irreducible quadratic factors? So repeated irreducible quadratic factors are the same idea as repeated linear factors, okay? If it's got a power, you have to go down as many as it takes. So in this case, I've actually got a pretty nice little simple looking denominator, but the numerator is kind of gross. And of course, if you look at this, of course, this is x to the fifth, so it's going to be gross. All right, so this is not the sort of, I mean, here you go. Let's just set this up and talk about it. So what you're going to have here, of course, this x is just like a nice little linear guy, so he just sits there. And then I'm going to have x squared plus 1 squared. And then because he's repeated, I have to go to have just x squared plus 1 and no squared. I need as general as possible kind of thing for my decomposition. This guy's going to be a, but both of these, because it's an x squared, it's supposed to be the bx plus c form. Bx plus c and then dx plus e. Okay? You don't have to square this top part. You just want to let the top be bx plus c, no matter how much this bottom part, squared, third, cubed, whatever. But, so this form just goes from the fact that this is an irreducible quadratic. All right, so you can see this is going to be a joy. Really fun integral. Great way to spend your Friday night, right? So that being said, I wouldn't actually put this on a test or a quiz, of course not, because it's to take forever. You'll see it is not, and it becomes kind of non-trivial, all right? But so that said, if you don't want to watch this, you don't have to watch the rest of this video. The thing that you need to take from this part is just when you have this, right? When it's repeated, you just have to keep going down the same way that you would go down with a linear one, only each time it's bx plus c. In practice, if you did this, it'll end up you'd be putting it into a computer anyway. This actually we can do by hand. The algebra here and the system comes out pretty easily, but it's the integral that's a pain. So it's kind of interesting to see. So I'm just going to get started and do this. All right. My bottom part here is that. Now a, of course, has to be multiplied by x squared plus 1 squared. The bx plus c has to be multiplied by x. And then your dx plus e here gets an x, but also a factor of x squared plus 1, because there's only one x squared plus 1 here. So this becomes ax to the 4th plus 2ax squared plus 2, messed up already, just a, right? And then here, this one's not too bad, bx squared plus cx. And then we have to remember that there's this x in here. So hold on, this would be x cubed plus x. So then I have dx to the 4th plus ex cubed plus dx squared plus ex, right? So all that. So for the x to the 4th, I have a plus d, that's here. For x to the 3rd, I have e. For x squared, I have 2a plus b plus d. For x, I have c plus e, right? And then for the constant, I just have a. Whoop, that doesn't look very good. That's a. All right, so let's put these up somewhere where we can see them. A plus d equals 5. Okay, there's no x cubed term over there, so e equals 0. Great. 2a plus b plus d equals 7. C plus e equals 1. And then very nice, a equals 2. Okay, so we can kind of pull these out a little bit. I know a equals 2, e equals 0, right? But then c plus e equals 1, so c equals 1. So if a equals 2, then d equals 3. And that leaves us with b. So what is this? b equals 7 minus 2a minus d. So 7 minus 4 minus 3, which is 0. Yeah, okay, that's right. All right, I believe, yes, that's what I got. Okay, that's right. So that's what it turns out to be. So let's write up our integral, and then we'll get rid of all this algebra, and then we can do this integral. So 2 over x plus, so b was 0 and c was 1. This is the one that's going to cause us some trouble and heartache, huh? X squared plus 1 quantity squared. Now d was 3, 3x over x squared plus 1. Okay. So we're going to leave those up there. And let's talk about that middle integral. Well, first of all, the first integral is natural log of x. The last integral is going to be natural log of x squared plus 1. That middle integral is going to be our toughie. It's not inverse tan because of this square. Okay? But thinking about inverse tan, it looks very similar, right? So in fact, what this one you need to do this one, you need to do a trig substitution. Okay? So, because now it's kind of weird, right? Because it's not a square root, but really it's like the square root of x squared plus 1 now to the 4th. Okay? So let's just play with this for a few minutes. This is what I have. And I'm thinking of this in terms of wanting to do it as a trig substitution. So x squared, and I'm thinking about that like it would be the square root of x squared plus 1. So in that situation, because we just were talking about this, right, it's x squared plus 1, square root of x squared plus 1, so that's going to be on the hypotenuse. So square root of x squared plus 1 here, and we can do x and 1 there. Okay, well that makes sense, because then tangent of theta is x over 1. So x equals tangent of theta dx is secant squared theta, and then this square root ends up being secant, right? Because cosine of theta is 1 over the square root. So the square root, I'll just write it here. It's going to be my secant of theta. So what this is going to be is the square root fourth, square root of the fourth, right? Get this right. And then, so I've got secant squared theta d theta here. This guy is going to be secant to the fourth down here. And okay, so that's not so bad, right? Because this is d theta over secant squared theta. So that's really cosine squared. And we know how to do cosine squared. That's just half angle. So I've got 1/2 cosine, right? So it's plus 1/2 cosine 2 theta. So then that becomes theta over 2 plus 1/4 sine 2 theta, right? So what we're going to do, though, again, now we have that same issue as we had in one previous problem. This is going to be like sine, well, 1/2 sine theta cosine theta, right? Because we can't read sine of 2 theta directly off the triangle. We need to turn it, right, into something we can read off the triangle. In this case, we didn't do a lot of work with the triangle too much. So, I mean, we did just this. So we're going to have to read off both the sine theta and the cosine theta from this thing. Okay? It's going to help me. But first of all, I'm going to go here. I'm going to get that theta is the inverse tan of x, which is kind of nice. Back to the purposes of the problem, right? So this kind of looked like inverse tan, but not quite. It has inverse tan with that square root, with that square in it. So, okay, I do get an inverse tan back, so that kind of makes me feel better. That maybe I'm on the right track here. So for the sine is opposite over hypotenuse, and cosine is adjacent over hypotenuse, so that's going to be x over the square root times 1 over the square root. But square root times square root is just going to give you the thing back. So if I rewrite this mess, we're going to rewrite it. I'm just going to rewrite it down here, I guess. But you know what? What I'm going to do is I'm going to rewrite it up here. Okay? I'm going to get rid of this. And we're going to write it right in the middle here. So for this middle integral, which is what we were doing, we end up with 1/2 inverse tan of x plus 1/2 x over x squared plus 1. And then for this piece, right, this is 2 natural log of x. And for this piece, again, it is natural log, right? But we have the x squared, so you get the 1/2. So I have 3/2 natural log of x squared plus 1. So finally, after all of that, that's my answer.